When we move from 4G to 5G, one of the most important things that we need to consider in the 5G RAN design is scalability. In 5G, we have a lot more spectrum available than what used to be available in the 4G days. And also the spectral efficiency itself is many folds compared to what was there in 4G. So overall, 5G as a technology is able to support much more bigger capacity than 4G networks. So when we move to 5G RAN network design, 5G RAN design, designing a very scalable, highly scalable 5G RAN software becomes a very, very important aspect and a differentiating factor when it comes to 5G RAN product development. Thankfully, 5G RAN is also increasingly being hosted on large-scale general-purpose processors where there are a lot of cores available to run the 5G RAN on. This is very different from the earlier days when we used to have embedded systems with fixed number of cores, usually limited number of cores. Now it is very different. The trend is to host the 5G RAN on virtualized platforms where there are a lot of cores made available to host the 5G RAN. But the complex part here is how do we design the 5G RAN software so that it is able to utilize all of these cores and scale to support multiple magnitudes of scale than what used to be possible in 4G. So we're looking at thousands of connected users. We are looking at 20, 30 UEs per TTI. So basically UEs per TTI or scheduled users per TTI has a direct influence on the latency and especially services like VoLTE and all that. So it's very important to serve 20 or 30 scheduled users per TTI. Then number of cells, like with 5G, carrier aggregation allows you to have 16 component carriers. So number of cells also increases. And of course, from all this comes throughput. So gigabit speeds is very, very common in 5G. So overall, you have a lot of users, a lot of scheduled users per TTI, a lot of cells and a lot of throughput. So all of these things to support that, and you have a lot of cores. So how do you make it happen? How do you design the software to make use of all of those cores and serve that kind of capacity that is demanded by 5G networks? This is a very interesting topic, and there are many software design patterns that are being used in the RAN industry to support this kind of massive scaling of RAN software. And I intend to have a series of videos in which I talk about the different design patterns. In this first video, I'll touch upon one of the most important design patterns when it comes to scaling 5G RAN, and that is called as the TTI pipeline. Now, first, let me talk about the pipeline design pattern. Now, the pipeline design pattern is a very common design pattern which is found in every kinds of software design. It is inspired by the assembly line. So in an assembly line, what happens is a product is being built in stages. So one stage does some part of the processing of the product, then it hands it over to the next stage which does something else on the product. It hands it over to the next stage where something else is done on the product, and so on until the final stage when the product is made and packed. So that's a typical assembly line. So in software design also, you see a lot of examples where you have a series of tasks or threads that are arranged in a pipeline, in an assembly line fashion, where the first stage does some processing, some functionality, and then it hands it over to the next stage which does some more functionality, and so on and so forth until you reach the last stage, after which the entire processing is completed. So this is called as a pipeline design pattern. It's very common in software, you see it everywhere. But when it comes to 5G RAN, we have adopted the pipeline design pattern, and we have our own TTI pipeline, which is basically the pipeline design pattern adopted to 5G RAN software design. Now, what is the TTI? TTI is the transmission time interval, which is a very important concept in wireless, which basically is nothing but the periodicity in which transmission is being done to the users from the radio access network. So every TTI, some data is sent to the users, and that is the periodicity. Now, behind the scenes, for every TTI, for the data to be sent out, there's a lot of processing being done to get this data ready for every TTI. And that processing could be like selecting what users need to be scheduled for the TTI, allocating resources for the users in a fair manner based on QoS and all those policies, then preparing the protocol headers and transport blocks to be shipped out to the user, coding it, and then shipping it out over the air to the user. So that entire behind the scenes work is happening to get the data out in every TTI. Now, in the TTI pipeline, simply put, is basically a pipeline where all of this behind the scenes work is arranged as a pipeline of stages, pipeline of work, which basically leads to the transmission time interval sending out the data. And this behind the scenes work can take multiple TTIs. Like, say, for example, the requirement we have is every TTI data has got to be shipped out. But you can arrange parallel processes running, like many of these trains running, so that each train delivers some data out in every TTI. But each train itself is composed of multiple TTIs and stages of multiple TTIs. So that, in essence, is the TTI pipeline. A better way to explain this is by actually showing you the TTI pipeline, the different functional blocks that make up the TTI pipeline in 5G. So I will explain this with explaining the DU software. In an ORAN architecture, you have the DU, which is basically hosting the layer 2 functionality. I'll explain the pipeline when I talk through the functional blocks of the DU itself. Right? I'll do that by tracing the flow of downlink packets through the DU and the uplink packets through the DU. Right? So let's start with the downlink packet. Right? So the downlink packet comes from the CU, into the F1U module. Now, the F1U module is basically terminating the GTP packets coming in from the CU, and it is decapsulating the GTP header and preparing an RLC SDU, and then it ships it off to the RLC module. Now, in the RLC module, in the DU itself, is split into two parts. The real-time sensitive portion of RLC, which is normally called as RLC lower, and then the non-real-time portion of RLC, which is called as RLC upper. So here, this is your RLC upper. So this is not TTI bound, like this work that this RLC module does, which is the RLC upper does, doesn't have to be completed in the same TTI. It can take a few TTIs, for example, so that it's non-real time, right? So then the data is given to the RLC upper. So RLC upper hosts the RLC state machine itself, like the AM state machine. It has that the window, the moving window, all of those logic is implemented in the RLC upper. Retransmission logic, everything is implemented RLC upper. So he runs the packet through all of those things and figures out whether this RLC packet that came in is within the transmission window. We can actually send this packet out, or all that determination is done. And if it determines that this RLC packet can actually be sent out, then he creates what is called as a buffer occupancy. Buffer occupancy request to the downlink scheduler module. Now, I'm just talking about the functional blocks here. I'm still not come to threads and all that stuff. Just look at the functional blocks. This is a downlink scheduler. So basically, what's his job? His job is to apply the scheduling policy. It could be a QoS scheduler, in which case QoS policies are applied. It could be a PFS scheduler. It could be a round-robin scheduler. Whatever it is, it applies some policy by which it decides among the multitude of users, thousands of users that are connected to this particular RAN, which among those users should should get some data served in this next TTI. That's what it is deciding. And for that, it has a lot of algorithms. And with that, it decides that, okay, I'm going to pick, like suppose if I'm supporting 20 UEs per TTI, I'm going to pick 20 UEs in this particular TTI to be scheduled based on some policy. And then I will tell my decision to the resource downlink resource allocator. Resource allocator module. Now this downlink resource allocator, basically what it's doing is it is allocating PDCCH and PDSCH resources to the UEs. Right? So he gives the decision, the scheduling decision, the selection of UEs to the resource allocator. The resource allocator does the job of allocating resources to all of them. And after the resource allocation is done, the decision of the resource allocation is passed on to, now we're just following the downlink path, okay, to a DL multiplexer entity. So what is the job of the DL multiplexer? So DL multiplexer's job is he is getting the inputs from the resource allocator. He knows exactly how many bytes are allocated to each user, and for each user there could be a multitude of logical channels. They could be like an SRB, couple of SRBs and multiple DRBs, all of them having data, right? So now the DL multiplexer further does the job of distributing the grant given by the resource allocator to that particular user between that user's logical channels. He will do that based on some policy that he adopts. He will say that, okay, I'm going to give 30% to this logical channel, then another 30% to this logical, another 30% third logical, like that, whatever scheme he employs, right? And that's his job. And then after that multiplexing is done, further the next module that comes is the RLC module. Again, RLC, this is RLC lower. We had talked about the RLC upper. Now this is the RLC lower, which is real-time sensitive. And this is the non-real-time part of the RLC. So real-time part of the RLC, which is RLC lower, gets the MUX would have distributed the grant between the logical channels and given its decision to RLC lower. Now RLC lower's job is, it will basically pull data out of a queue, and this is your RLC SDU queue. Pulls data out of the RLC SDU queue, which is filled by the RLC upper. So as the data comes from CU through F1U to RLC upper, the data is queued onto the RLC SDU queue, which is per UE entity. For every UE, there's a different, for every UE, every bearer, there's an RLC SDU queue. And there could be multiple RLC SDU queues here if the UE has got multiple bearers. And the RLC lower entity, based on the decision given by the MUX, will pull out that many SDUs or parts of the SDUs from the SDU queue, form RLC PDUs, and after forming the RLC PDUs, it will basically populate a data structure, which is like, you know, a TB data structure with only the RLC PDUs, and then gives the output, the RLC PDUs, to the MAC TB creator entity. So this guy's job is to create transport blocks. So if there is, for example, 4 component carriers with MIMO, like with two TBs per 2 layer, like 4 cross 4 MIMO and 5G, then he could have like 8 TBs to be created for that user to be served in that particular TTI. And the MAC TB creator will take all of these RLC PDUs, which are packed into the TB structures, and he could also be getting some MAC Cs to be scheduled to the user in the same TTI. So he'll combine MAC Cs, RLC PDUs and all, make the full TB, which is a MAC transport block, and then he will send it to the FAPI transmitter. So the FAPI transmitter is basically the guy who ships the data to layer 1. And all of these TBs are given to FAPI, and then FAPI transmitter layer ships it out of the PHY, usually via DMA or some of these kind of mechanisms. He'll push it out to the PHY. So this is the overall flow. Like if you look at it, the packets came from the CU, they got processed by FNU, RLC upper, then the scheduler decided which UEs get scheduled at what time, then resources got allocated for downlink resources, and the multiplexing happened, the RLC PDU creation happened, MAC-TB creation happened, then the data got shipped out to PHY. It came from CU, it went out of the PHY. So you're done with the downlink flow, right? Now let us come to the uplink story. Like what happens, how does uplink flow line up in this whole set, right? So here uplink flow usually happens by the UE saying, boss, I've got some data to transmit, so how do I do it? Like give me some grant, right? And how it does that is, you have now everything from the UE comes via PHY through the FAPI receiver entity now. So this also, he will receive data from the PHY, and one of the important data here is SR, which is scheduling request. The UE is saying schedule something for me. I need to transmit in the uplink. So he's sending SR, or it could be BSR, or basically he's just trying to say, give me data, give me a grant so that I can transmit something in uplink via buffer status report or scheduling request. Any of these mechanisms he will send it, and it comes to the uplink scheduler. Another important input for this uplink scheduler is CRC indications. So this UL CRC indications basically say that some uplink data got transmitted, but that was in error. So we'll have to schedule retransmissions. So that also is an input that UL scheduler needs. So UL scheduler now has got what UE should I consider for retransmission in the uplink? What UE should I consider for new transmission in the uplink? So he's got a data of all the uplink users who have data to transmit, either transmission or retransmission. And then he applies some policy, based or round robin, whatever, and then decides that n number of UEs will be scheduled in this TTI, and they'll be given this much of data, this much of grants, scheduling grants. So then the uplink scheduler will tell its decision to the downlink scheduler, the downlink resource allocator. This is because even the uplink grants are given via PDCCH transmission, where the PDCCH carries the uplink grant, and that PDCCH is allocated by the DL resource allocator. So the UL scheduler will get all of this. He'll make his decisions as to these are the UEs to be scheduled, tells that decision to the downlink scheduler, so that PDCCH DCI zeros can be allocated for all of those UEs, either new transmission or retransmissions. After that, once the PDCCH for uplink is allocated by the DL resource allocator, then the transfer goes into a uplink resource allocator. This guy is in charge of allocating PUCCH, PUSCH resources to that UE, or about a bunch of UEs selected in that TTI. And once that allocation is done, this whole data now is given to the FAPI transmitter in the form of UL config. So UL config basically tells the PHY layer that now, okay, I would have transmitted this PDCCH, so there's some uplink data expected in this given TTI, in this particular TTI. So you expected, you report me whenever that data comes. He's telling that to the PHY. So that is done by the UL via the UL config FAPI control message sent to the PHY. Now, once it is done, now UE gets the PDCCH, which is DCI 0. Then whenever that uplink grant is given to him, in that given TTI, he will transmit the uplink. And that uplink transmission again comes from PHY and as a TB, and that goes into an entity called as UL demultiplexer. So UL demultiplexer get all the TB, uplink TBs coming from the FAPI. He will strip out the maxis in that. There's the maxis could be sent to either uplink scheduler, downlink scheduler for further processing. And the data blocks, which is the RLC data that is coming in the UL demarks, is now sent to directly to the RLC upper. There's no RLC lower. RLC lower is a purely downlink entity. So the uplink data is always non-real time. It's in a non-real time path because nothing is TTI bound in uplink. It can be non-real time. So that data is sent to the RLC upper. The RLC upper will basically strip off the RLC header, get the inner data, and then sends it to the F1U. F1U will further encapsulate that in the GTP header and sends it out to the CU. So this is the flow of the uplink data. So now what we have seen is we have seen the flow of downlink data through the DU, uplink data through the DU. Now we just looked at all these as functional blocks. Now the problem statement for us now is how do we distribute all of these functional blocks that we have seen, which basically form the layer 2 of 5G RAN into multiple cores and multiple TTIs. And we'll see both extremes, right? One extreme is assume there is only one UE to be served, right? Then why do we even bother about why do we need so many cores to handle all this? We can just do the entire thing in a single TTI and host all of these modules in a single core. So basically you get data from the DU, you run through all of this processing and then send it out of the PHY in the same TTI. Because we don't have much scale, it's just one UE, there's not much decision or processing to be done here. Take the other extreme. Say you have 1,000 connected users, 1,000 active users, and we are going to serve 20 users per TTI. Now, if you look at it, the scheduler has to basically select top 20 users among 1,000 users based on whatever policies it runs and ranking it does on the UEs. It selects the top 20 users and then it has to allocate resources, PDCCH and PDSCH for all of these 20 users, and then it has to multiplex data for all of these 20 users. And say you also have, for example, 16 component carriers also. That also further, like you have to do resource allocation of 16 carriers for every user, every 20 users. So basically all of these blocks become very fat when there is a lot of scale to be supported. So they cannot run in the single core in the single TTI. They cannot complete the entire work in a single TTI on the same core. It's impossible. So then you may have to basically split this into multiple tasks and threads, put them on different cores and also on different TTI, so that each block gets an entire TTI to run and make the TTI pipeline longer. So let's look at that extreme. How might it look? So I could, if I take the extreme case, right, I can say FAPI RX can be in one TTI, then this UL scheduler and UL scheduler can be in another TTI, DL scheduler can be in the third TTI, DL resource allocator in the fourth TTI, then the DL MUX entity and the UL resource allocator can be in the fifth TTI running in parallel, and RLC lower can be in the sixth TTI, MAC TB creator in the seventh TTI, FAPI TX in the eighth TTI, and then to 5. So basically you can make a 8 TTI pipeline. So there is eight TTIs to run through all of these blocks, right? So that's the longest pipeline that you can envision. But if you do that, of course, now every module gets a full core for itself, and it also gets the entire TTI to do its processing. So it's a max scaled out vision that we've got, right? But it comes at a cost. So the cost is that one thing you see is if you have 8 TTI pipeline in layer 2, then you add the PHY delay and all that stuff for the few more TTIs for PHY processing, you end up with a very large latency in the overall processing. You add latency to it, many TTI latency. Also, you could also get to a point where you could suffer in single UE throughput, because in single UE throughput, if your HARC round trip time has to be quick enough so that you don't run out of 16 HARC processes. So it should be less than I think 18 or 19 TTIs. If the round trip time is not within that window, then whenever you schedule in all the 16 TTIs, you finish up all the HARC processes, the first HARC processes, first transmissions heart feedback wouldn't have come because of the delay that we introduced here. So you will end up wasting some TTIs. So single UE throughput for that particular user. So single UE throughput will be limited. It will be coming down if we have too many stages in the pipeline. But it's a trade-off. So you can sacrifice single UE throughput, you can sacrifice on latency to achieve massive scales by going for very long pipelines. Or you can, based on your profiling results, you can settle at some midpoint here, right? So for one of the options could be that let's do, for example, let us do this whole FAPI receive, uplink scheduling, downlink scheduling, and downlink resource allocation, all of these things in one TTI. And so this is TTI N and this is TTI N plus 1. N plus 1 we do the rest of the stuff. That can be one option. And if all of these entities are hosted in a single thread, for example, and they are working in the same TTI, and that processing power that is given by that single core is enough for running all of these things in a given TTI, then we can go with this approach. And suppose we say that, okay, now we're not able to do this, the scheduler is taking too much time, we can even create one more stage here. Say this can be n, this can be n plus 1, this can be n plus 2. And further, if say for example you come to a point where, okay, all this is fine, let's make one more stage here because we are scaling higher, and we can go for n plus 3. So we end up with a 4 TTI pipeline. So there's a lot of flexibility here. Now the thing that we have to do is the interfaces between each of these functional blocks should be such that it doesn't matter whether that interface is across a TTI boundary or within the same TTI boundary. So you got to design data structures between these entities in such a way that if you change that, you put them in one TTI and another one across the TTI boundary, or put them in the same TTI, it should not make much of a difference. So the data structure design there is very important, and the data structure design also should be lockless. So even if they're running in different cores, you can make it lockless by having slot-based containers. So that's another design pattern. I'll talk about that later. So this is the TTI pipeline design pattern. You have a lot of flexibility here, as you can see. You can make multi-stage pipelines, you can make multi-TTI pipelines, and also number of TTIs of this pipeline, the length of the pipeline, all of these things are adjustable based on the scaling demands of that particular 5G RAN deployment. Another important thing to consider here is this design should ideally be dynamic and adaptable. So by that, what I mean is, like, say, example, in peak hour, you may have massive scaling, right? Because a lot of users, so you may have to run at peak capacity. So then you could go for a multi-stage pipeline, like with so a lot of stages in the pipeline. But say at night time when there's nobody, and it doesn't make sense for you to be running hot on all of these cores with so many pipelines and introducing unnecessary latency and all that stuff. You should be able to collapse this dynamically into fewer number of TTIs, or even a single TTI pipeline, single stage pipeline, if need be, when at off-peak hours. So the software should be very, very agile and flexible, so that you can go for the max case or the min case without in a dynamic, configurable manner, so that you can adapt based on the demands, the dynamic demands that are in the network. So that's probably gives you a good summary of what a TTI pipeline design pattern is. It's a very, very important design pattern. Now, I've touched upon most of the blocks in layer 2 on the DU side. Now, there are many, many other design patterns. In that, we'll touch upon other blocks as well, which I haven't covered here in more detail. So for now, this is all I had for today. Just wanted to cover the main important design pattern of the TTI pipeline. I hope this is clear, and I hope I haven't left out anything, but please feel free to comment and ask me questions. I'll be very, very happy to answer or enter into any kind of discussion on this topic. It'll be good for my own expansion of my knowledge based on your experience. If you've seen something, if you want to comment on something which is interesting in this area, please feel free to comment on it, or any questions, please let them come my way. Thank you very much for your time, and hope this has helped you understand an important aspect of 5G RAN design. That's all for today. I'll see you in the next video. Thank you very much, guys.